All right, welcome. Today we're diving deep, and I mean really deep, into one of Cisco ACI's coolest features, multipod. We're going to take all that dense documentation and turn it into something you can actually use. By the end of this, you'll have a solid grasp on how these things are built and, more importantly, how data actually gets from point A to point B across different locations.
So let's kick things off with the big question, right? The whole reason multipod even exists. Imagine you've got this amazing, powerful ACI fabric running in your data center. It's awesome. But now you need to expand. You need a presence in another building, maybe across campus, or even across town. How do you do that? How do you stretch that single fabric across multiple spots without creating a total management nightmare? That's the puzzle we're tackling today.
Okay, so here's our plan. First, we'll talk about what multipod is and why you'd use it. Then, we'll get into the fun stuff, the automated provisioning. After that, we'll look at the control plane, how the pods talk to each other, and the data plane, how the packets actually move. And we'll wrap up by figuring out how the fabric finds devices, even the quiet ones.
All right, Section 1. Let's start with the big picture, scaling ACI with multipod. We're going to cover the why behind this whole thing.
Now, this is absolutely key, so listen up. Multipod is not about gluing two different ACI fabrics together. Think of it more like taking a single piece of elastic fabric and stretching it over multiple points. It's still one logical fabric, all managed by one APIC cluster. That's your single brain. And what connects these points? A regular IP network, which we call the interpod network, or IPN. The result? You get to operate in multiple locations, but from a single pane of glass with one set of policies. It's a game changer.
Okay, so we know why we want it. Now for Section 2, automated pod provisioning. Let's dig into how you actually expand the fabric.
Okay, before all the automatic magic happens, you do have to do a little bit of prep work. There are 3 things you got to get right. First, you've got to set up the access policies for the spine switches that connect to your IPN. And pro tip, it has to be VLAN 4, no negotiation on that one. Second, you need to define the TEP address pool for the spines in the new pod. And third, and this is the big one, your IPN needs to be ready. That means it's got to have OSPF running, PIM for multicast, and here's the secret sauce, a DHCP relay agent. That DHCP relay is what makes the whole automated discovery process work.
And boom! Once you've got those prerequisites locked in, this is what happens. It's pretty much hands-off from here. This whole process just kicks off automatically. Let's walk through these steps and see exactly how a brand new unboxed pod comes to life and joins the party.
Okay, so here's the play-by-play. A brand new spine in Pod 2 powers up. The first thing it does, it screams out a DHCP discover request. Our handy DHCP relay in the IPN grabs that request and forwards it all the way over to the APIC in Pod 1. The APIC acts like the director, right? It replies with an IP address and says, hey, here's where you get your startup script. The spine downloads its config, gets its routing up and running, and then, this is cool, it becomes the DHCP relay for its own pod. From that point on, all the other leaves and spines in Pod 2 just boot up and get their info from that first spine. It's like a domino effect, a perfectly automated cascade.
So, our pods are up. They're connected. But now for the real question, how do they talk? How do they share info about who's connected where? That brings us to Section 3, the interpod control plane.
Okay, before we connect the pods, let's talk about what happens inside a single pod. The source of all truth is something called the SOUP database. SOUP stands for Council of Oracle Protocol. Fancy name, right? But just think of it as the fabric's GPS. It lives on the spines, and it maps every single endpoint, every IP and MAC to its exact location. When a leaf switch sees a new device, it just tells the spines, and they all update their maps. Simple as that.
So, how do we get those maps shared between pods? We use NBGP EVPN, but to make that work, ACI uses a few special addresses, or TEPs. First, there's the BGP router ID. That's just the spine's name tag for the BGP conversation. Then you have the DP TEP, the data plane TEP. Think of this like a zip code for the entire remote pod. And finally, there's the Anycast proxy TEP. This is like the specific mailing address or PO box you send packets to when they need to cross over to that other pod.
And this is where it all clicks together. We see the journey of information from a device in Pod 1 all the way to the brains of Pod 2. And what's really brilliant here isn't just that the info gets shared, it's how it's abstracted. This is the secret to making the whole thing stable and scalable. Let's follow the data. So, check this out. Step 1, an endpoint EP1 shows up on a leaf in Pod 1. Step 2, that leaf immediately tells its local spines via COOP, The spines say, got it, EP1 is on this specific leaf. Step 3, the Pod 1 spines then use BGP to tell the Pod 2 spines about EP1. But, and here's the magic trick in Step 4, they don't say EP1 is on leaf 1. No way! They just say, to get to EP1, send your traffic to Pod 1's general delivery address, which is that Anycast proxy tab. Why is this so smart? Well, it means if EP1 moves to a different leaf inside Pod 1, Pod 2 doesn't care. No new BGP updates are needed. The control plane stays super stable. It's genius.
Now, when you're setting up this BGP conversation between the pods, you've got two main options. The default is full mesh. Think of it like a conference call where everyone is talking to everyone else. It's simple to set up for a few people, but it gets crazy chaotic and inefficient as you add more. The much smarter, more scalable way is to use route reflectors. This is like having a designated speaker in each pod. All the other spines just talk to their local speaker, who then communicates with the speakers in the other pods. It's way cleaner and the recommended way to go for pretty much any real-world deployment.
And the best part? You don't have to be a BGP expert to do this. ACI makes it incredibly simple. Inside the APIC, when you're adding a new pod, it's literally just a choice between two radio buttons, full mesh or route reflector. You click one, and ACI handles all that messy BGP configuration in the background. It's all about making complex networking easy. Okay, control plane is sorted. The maps are shared, everybody knows the general location of everybody else. So now for the action. Let's get to Section 4 and talk about the VXLAN data plan, how the actual packets get from A to B.
And here's the thing you have to remember. It's all about efficiency. Once the endpoints know about each other, the traffic doesn't take some weird scenic route through the spines. No way. It's a direct shot. A VXLAN tunnel gets built directly from the leaf switch in Pod 1 to the leaf switch in Pod 2. The spines in the IPN in the middle, they just become the highway that this tunnel travels over. It's a direct, point-to-point data expressway.
Okay, but wait. This all works great if the fabric already knows where everybody is. But what about a brand new device? A silent host that's just plugged in. It hasn't said anything yet. How in the world does the fabric find it, especially if it's in another pod? Let's solve that mystery in our next section, Endpoint Discovery in ARP.
So to really see how this works, we're going to take the trickiest possible scenario. Let's say we've allowed ARP flooding on our network, and we have EP1 in Pod 1, and it needs to talk to EP2 over in Pod 2. But the fabric has absolutely no idea that either of them even exist yet. Total strangers. Let's see what happens.
So here's phase 1, the search party. EP1 sends out an ARP request, basically yelling, "Where's EP2?" Its local leaf has no clue, so it wraps that ARP request up in a multicast packet and sends it up to the spines. The spines then send it out everywhere within Pod 1, and they forward it over the IPN as a multicast message. The spines in Pod 2 get it, and they send it down to all their leafs. Eventually, that message finds its way to the right leaf and finally reaches EP2. And here comes the answer. As soon as EP2 gets that message, it sends back a reply. "Hey, I'm over here." Now, this is the smart part. That reply is not flooded. Its local leaf switch sees the reply, learns exactly where EP2 is, and immediately tells its spines. Then, it wraps that reply in a direct unicast VXLAN packet addressed straight to the leaf where EP1 lives. Once that first leaf gets the reply, the connection is made. Both devices are now known in the fabric, and from this point on, all their traffic will be direct and efficient.
Now, let's be honest. Flooding traffic all over the place isn't always the best idea. It can be noisy. So, what if you disable ARP flooding? Does everything break? Nope. The fabric has another, more elegant solution. It's called ARP gleaning.
So here's how gleaning works. When the fabric sees traffic going to an unknown device, instead of just blindly flooding it, the spine itself steps in. It creates its own ARP request, pretending to be the gateway, and sends it out on a special multicast channel looking for that silent host. This lets the fabric actively go out and find the device, wherever it is, and kickstart that same learning process we saw before, but without all the initial flooding noise. It's a much cleaner way to do discovery.
So, when you step back and look at all this, the big takeaway isn't just about protocols and packets. It's about a fundamental shift in how you run a network. You're no longer babysitting boxes in different buildings. You're managing one, single, intelligent fabric that spans locations. When the network itself can handle the discovery, the configuration, and the connectivity across huge physical distances, well, that frees you up to think about the bigger picture. You can focus on the services, the applications, the things that actually drive the business. So the final question I'll leave you with is this. Now that the network can do all this, what are you going to build on top of it?